The compiler functions are: compile a module to bytecode, compile a fire and forget query to bytecode, parse a module returning a module instance, which is the object model of a module and contains all module information. Validate module syntax. Parse a statement returning a EP statement object model, which is the object model of a statement and contains all statement information. The compiler is a stateless, thread-safe service. The runtime hosts and executes the bytecode produced by the compiler. A module contains statements that are separated by semicolon. Modules cannot be used for fire and forget queries. Modules may optionally have these keywords. The module keyword can provide a name for the module. The uses keyword can list dependencies of the module on other modules. The import keyword can list dependencies of the module on class path. This box below highlights a module text that showcases all module keywords. The text module.com.mycompany.mymodule assigns the module name. The text uses com.mycompany.someothermodule indicates that the module relies on some other module that it requires. The text import org.mycompany.mypackage indicates that the module relies on classes that reside in the package org.mycompany.mypackage. When import is not specified, any classes that the EPL uses must have the fully qualified class name. Imports can also be configured as compiler configuration. This sample module has two statements. The first statement of the sample module defines an event type with create schema. Note, defining an event type is covered later and this module does not define the event type visibility in the bus modifier. The second statement of the sample module selects all events of the defined type. The text uses keyword can avoid name conflicts and automatic deployment can use this information to determine deployment order. EPL objects are objects that can be shared between statements. The full list of EPL objects is: event types, variables, named windows, tables, contexts, expressions and scripts, indexes, inline classes. A statement can create a new EPL object. For instance, create schema my event type. A statement can use existing EPL objects. For instance, select star from my event type. Some EPL objects can be preconfigured. EPL objects have visibility rules that define whether other modules can see the EPL object. The private visibility is the default. An EPL object with private visibility is visible within the current module only and is not usable by any other modules. The protected visibility is for use with module names. An EPL object with protected visibility is visible to modules with the same module name only and is not usable by any other modules that do not have the same module name. The public visibility is when an EPL object is simply visible to all. An EPL object with public visibility can be used by all other modules. EPL object names do not have to be unique across the runtime, since with visibility rules you can decide a scope. Event types also have an event bus modifier, discuss later. The compiler options have flags that set the default visibility and the event bus modifier for event types. The compiler resolves EPL objects from a path and according to visibility. We'll discuss the concept of compiler path later. The compiler can resolve EPL objects from an existing runtime's deployments. This slide discusses how the EPL objects and class path dependencies are tracked by the compiler and validated by the runtime. For EPL objects, the compiler adds a module's dependencies on other EPL objects into the compiler output. The compiler output contains the EPL object names and module names that a module depends on, if any. The runtime validates that EPL object dependencies exist before deploying a compiled module. The runtime does not validate that the information about the EPL object is the same as at compile time. Therefore, in development, changes to public or protected EPL objects should be tracked like changes to interfaces or superclasses. In respect to class path dependency tracking, the compiler outputs bytecode that imports and uses application classes. The runtime does not validate class path dependencies, however the JVM class loader resolves them on load. Therefore, in development, changes to public or protected application classes that are used in EPL should be tracked. The topic of this slide is the compiler programming interface. The first step is to obtain a compiler instance by calling the getCompiler method of EPCompilerProvider. The code snippet is EPCompiler compiler equals EPCompilerProvider.getCompiler. The second step instantiates a new configuration object. The code could also get an existing configuration object from a runtime or by loading it from a file with one of the configuration class's configure methods. Configuration configs equals new configuration. The third step instantiates a compiler arguments objects passing the configuration. Compiler arguments args equals new compiler arguments parenthesis configs. Now we are ready to compile. The compiler offers multiple compile methods depending on whether you are compiling in module string, or a module object, or a fire and forget query. Let's assume we compile a module string. The code to compile is EPCompiled equals compiler.compile parenthesis EPL, args. The output of the compile method is an EPCompiled that can be deployed. Multiple threads each use their own compiler instance. The compiler outputs an EPCompiled instance that contains the following information: a map of class name and bytecode, a manifest with internal information such as the compiler version. The runtime inspects the manifest and loads classes. When deploying an EPCompiled instance or when executing a fire and forget query. There is a utility class EPCompiled IOUtil that can write and read an EPCompiled instance to and from a file, in the jar file format. Let's talk about compiler arguments some more. The configuration that your application passes to the compiler arguments configures the compiler. The configuration can have pre-configured event types, variables and constants. The configuration has extension information for extending EPL with user-defined functions, application-provided aggregation functions and more. The configuration can set the default visibility for EPL objects and the default event bus modifier for event types. The compiler arguments instance has more functionality. The compiler arguments contain the path. The path is important as it tells the compiler about the EPL objects that the module may depend on. The path consists of EPCompiled instances and/or a runtime path obtained by the getRuntimePath method of an EPRuntime instance. The compiler arguments also has a compiler options instance that can compute and override names, visibilities and other settings. Please see the full API documentation, Java doc, or reference documentation for more information. The next section of the training is about the Esper runtime. The Esper runtime has these functions. The runtime is a target for EPCompiled instances. The compiler outputs an EP-compiled instance when compiling a module or when compiling a fire and forget query. An application deploys and undeploys compiled modules. When deploying a module, the runtime loads the classes, resolves EPL object dependencies, and starts the statements of the module. When undeploying a module, the runtime stops the statements of the module and releases the classes, allowing garbage collection to free the memory. An application can execute compiled fire and forget queries. When executing a fire and forget query, the runtime loads the classes, resolves EPL object dependencies, executes the query, and returns the query results immediately. Fire and forget queries can also be prepared for repeated execution. The runtime performs execution of time and events. The runtime determines, for incoming and insert into events, which statement partitions to execute. The runtime performs event execution for each statement partition that needs to see the event. The runtime determines, for time advancing, which statement partitions to execute. The runtime performs time execution for each statement partition that needs to see the time advancing. The runtime also provides EPL object-related services, such as the event type service, which returns event types. Statements and event beans also return the event type. Another example of a EPL object-related service that the runtime provides is the variable service for reading and setting variable values. In Esper, the runtime instance is central to executing event processing. A runtime instance is a stateful service. The list below outlines the types of state that a runtime manages. A runtime instance is uniquely identified by a string type URI. You can use any value as the URI. When no URI is provided, the value is the string double quotes default. Runtime instances are independent of each other. Runtime instances do not share any information with each other. A JVM can have any number of runtime instances. Most applications would use just one runtime instance. A runtime is stateful. The runtime state consists of these states. The runtime maintains the deployments. Deployments consists of the classes loaded for the deployment and deployment metadata. The runtime maintains statement state. Statement state can include aggregation state, pattern state, data window state, and more. The runtime maintains EPL objects. It keeps the event types, variables, context partitions, and more. The runtime maintains the current runtime time. The current runtime time is a long type value that is the current time, to be discussed. The runtime also maintains the prepared fire and forget queries. The topic of this slide is the API for Esper runtime instances. To begin, construct a configuration instance. The configuration object has all the default settings. Before obtaining the runtime, make changes to the configuration since the new runtime uses the information in the configuration object to initialize. The EP runtime provider provides runtime instances. The EP runtime provider is a singleton that manages URI values and associated runtime instances. A singleton is an object that exists only once per JVM. The EP runtime provider only has static methods on it, and there is only one instance of EP runtime provider per JVM. Allocate a new EP runtime instance or get an existing runtime instance by calling the getRuntime method and passing a URI and a configuration. For this example, the runtime URI is the string double quotes default. The code is EP runtime runtime equals EP runtime provider dot get runtime parenthesis URI comma configs. So, the first call to the getRuntime method allocates a new runtime instance. Calling the getRuntime method repeatedly and passing the same URI returns the same runtime instance. To get an existing runtime instance without allocating, use the getExistingRuntime method. The getExistingRuntime method returns the runtime for the given URI if it was already allocated, or returns null if the runtime was not yet allocated. Destroy the EP runtime instance when it is no longer needed by calling runtime.destroy. Note: updating the configuration after a runtime is already allocated has no effect on that allocated runtime. The runtime manages time, however time is still under the control of the application and time can come from events or other sources. Runtime time is a long type milliseconds value since Unix epoch, which is January 1, 1970 at 0 hours 0 minutes 0 seconds. Microseconds are supported too. To get the runtime time from a runtime instance, call runtime.getEventService.getCurrentTime. The EPL function that returns the current runtime time is current_timestamp. There are two options for moving time forward. Internal time follows the operating system clock. It is also known as system time. External time is when application code advances time. At runtime, the clock internal and clock external methods switch between internal time and external time. Time can only move forward, but time can be reset. Note: avoid blocking code, such as locking, I/O and networking code, in user-defined functions, extension code and listeners, since that may halt time advancing. This slide continues the discussion of time management and summarizes internal time. Internal time follows the operating system time. Internal time is the default setting. So when using the default configuration, the runtime uses internal time. When using internal time, the runtime starts a timer thread that follows the OS clock. That timer thread executes all time-related work for statements. The default resolution for internal time is 100 milliseconds. Note: make sure the application code is not also advancing time. JVM full stop garbage collection can also halt time advancing. Staying within the topic of time management, external time is when the application controls how time advances. In order to use external time, your application must set a configuration flag. The code for setting the external timer flag is configs.getRuntime.getThreading.setInternalTimer enabled false. The advance time method takes a long type time. The time is in milliseconds since Unix epoch, unless configuring microseconds. This method jumps time forward to the target time. Runtime.getEventService.advanceTime. The time passed is absolute time and is not relative time. So, for example, advance time (2000) and advance time (5000) for advancing time to second 2 and then to second 5. The time value can be any long type value and does not need to be related to system time at all. For example, use advance time (0) in unit or regression testing before deploying. This is handy in regression tests, to reset time to 0. The application thread that advances time executes all time-related work for statements, when using the default configuration. The advance time span method slides time forward to the target time, by internally checking which time is the nearest time to current time that work needs to be done. The advance time span method continuously moves time forward while the advance time method jumps to the target time. This slide discusses how to process events. A sendEvent method processes an event. Depending on the event representation, use one of these sendEvent methods. The sendEvent bean method processes an object event. The object's class is an application class. Use this when the event object's class is an application class. The sendEvent map method processes a map event. or dictionary in .NET C#. Use this method when the event implements the map interface. The send event object array method processes an object array event. The send event JSON method processes a JSON string. The send event XML DOM method processes a XML document event. So, to illustrate, assume the application has defined a withdrawal class that has a constructor that takes an string account ID and a numeric amount. The withdrawal class also has getter methods. To process a withdrawal event, the code is runtime.getEventService.sendEvent (withdrawal, event type name). The application thread that sends the event executes all event-related work for statements when using the default configuration. The slide has two topics. The first topic is the event sender interface. The second topic is the route event method. Instead of a send event method, the event sender interface is helpful when the event type is known in advance. The first step in using an event sender is to obtain the event sender passing the event type name. The code is event sender equals runtime.getEventService.getEventSender (withdrawal). This returns an event sender instance that can only process withdrawal events. The event sender throws an exception if sending any other kind of object. When processing a withdrawal events, call sender.sendEvent (withdrawal). The route events methods add events to be processed. The route event methods are only for use when listeners or extension code sends events. The route event method does not process events unless called from listeners or extension code. The route event methods avoid possible looping. The route event methods ensure that each event can be processed entirely before the next event gets processed. Here are two sample route events methods. Use routeBean when the listener or extension code has an object event to process. Use routeMap when the listener or extension code has a map event to process. The runtime processes each event completely before processing the next event. After processing an event or step in time, the runtime dispatches results to listeners and subscribers. Processing of consequences after processing an event works like this. Each thread has a thread local work queue. Events generated by insert into and routed events, from listeners and extension code, enter the work queue. The runtime next processes the oldest event or the highest precedence event in the work queue. For event precedence, see insert into syntax. And so on until the work queue is empty, and the thread returns from the send event method. Statements execute in any order unless using the @priority annotation. Statements do not execute in the order of the module or the order they were deployed.